of all, Happy New Year to everyone. Hope you had a nice, good start in 2004. Today I would like to welcome Professor Gregory Jablonsky from the Washington University. It's somewhere, it's Washington Department of Chemical Industry Engineering.
Yes.
In St. Louis.
St. Louis.
Professor Jablonsky was a former professor of the chemical engineering in Kiev, the Polytechnical Institute, and the Institute of Catalysis in Novosibirsk, very well known. He is an author of 6 books, including kinetic models of catalytic reactions. He is an organizer of many scientific conferences in the area of kinetics and catalysis, and he was a visiting professor at many universities, particularly I mentioned the Ben-Gurion University in Israel, University of Minnesota, École Polytechnique Montreal, the EPFL in Lausanne in Switzerland, University of Ghent, and the National University of Singapore. Professor Jablonsky will talk today on temporal analysis of products of the catalyst characterization and catalyst preparation. So I'm really very interested. I hope you enjoy the talk. Professor Jablonsky, please, what do you...
First of all, Dr. Ladeberg and all the members of this seminar, I am very thankful for this kind invitation. Really very appreciate to have this possibility, because I'm not going to exaggerate, but your seminar, Tri-State Seminar on Catalysis, it's well known because not so many active seminars in the United States. We have Chicago, New York, California, Tri-State universities, not so many. That's why it's really, with no exaggeration, it's an honor for me. Okay, so I will talk about what we have now. Okay. Where is title? The title is gone. Okay. The real title is, just a minute, Catalyst Characterization and Preparation Using Temporal Analysis of Products. This is like, do you know what is show me state? It's Missourian slogan. 2 minutes ago I explained Professor Ladeberg about this. And in fact it's very symbolic for us. The legend about show me state is the following. Missouri was proposed to join American state. Okay? State, and people who proposed tell, please join the state of freedom and prosperity. But Missourians were very suspicious people, and they asked, where is the state? Show me the state. Okay. But this talk will be very focused on what does it mean state of the catalyst. It's not easy idea to show state. Okay. So, we are talking about catalyst preparation and characterization. Let's start from catalyst preparation. I took this picture from a classical book, known book, Method for Preparation of Catalytic Materials. What does mean preparation? Blending, transforming, mounting, a mechanical procedure, and final catalyst. It's a series of typical procedures. But we have like a recipe. We don't have good procedure to characterize composition precisely. Okay? And then for catalyst we have bulk, catalyst preparation, precursor, drying, calcination. It's exemplified by known catalyst, VPO, for example, catalyst, vanadium oxide catalyst for selective oxidation. And then the main thing for catalyst, as you know, catalytic process occurs on the surface. So catalyst surface is the main thing. And we'd like to modify catalyst, for example, reduce or oxidize by oxygen, or modify catalyst by transition metals. Okay, but ideally we need to know precisely what's going on, what is changing in surface composition. So we are doing physical characterization, structure analysis. We are doing kinetic characterization using some probe molecules. And if we are adding atoms, we need to do the same thing. Okay, and catalyst, to prepare catalyst, we need to have precise characterization. And key challenges: we need uniform, precise coverage change, and we need kinetic analysis, which minimally perturbs the surface composition. So, first statement, my statement is no preparation with precise characterization. Okay. Without. Excuse me. Now, what does mean kinetic characterization? The next step, kinetic characterization. So, it provides basis to identify active selective catalysts, constructing kinetic models, elucidating kinetic reactor mechanism. In fact, it's not obligatory. And then, what is important, industrial materials usually multi-component. We have really complicated materials. This is the main problem. For example, in our case, selective oxidation, alkenes and alkanes, important examples are mixed transition metals. Okay? And also, catalysts can exist in different states. In different states. What does it mean in this case? It's function of oxidation degree, water content, they have different kinetic properties, they change when catalyst is exposed, etc., etc. Okay. So, in kinetic characterization, the main goal to extract the chemical transformation rates from reaction transport data and to determine the dependencies on catalyst composition and reaction and reactive mixture composition. In traditional CSCR reactor, open reactor, we are distinguishing convective transport and reaction. But in tap reactor, as I will explain you later, we are distinguishing diffusion transport and reaction. Okay, so rate is a function of three variables. One variable is gas concentration, coverage, and number of metals. For just more precisely, variables of the gas phase, set of gas concentration, variables of solid catalyst phase, set of, for example, number of metal atoms in catalyst, and variables that describe interaction between the gas and solid phases. It means a set of surface concentration. By the way, you can interrupt me anytime to create some feedback. If something, something wrong, I am going too fast, I appreciate it. Okay? So far? No. Okay. So now I'm straight for going to our device. Just present device. I'm going to present this device and some data, and then to depict, to describe this device on the background of different, I'd like to compare our device with different devices. This device, tap pulse response experiment, was invented about more than 50 years ago, initially in Monsanto company by Dr. John T. Gleaves. Okay? In fact, there is some link between this idea and the molecular beam idea, but what is main part of this device? You have inert zone, for example, 1, inert zone 2, quartz, and between you have catalyst. This 3 zone is constructed to guarantee isothermal character, just it's historically 3 zone. Okay, so you have wave, pulse wave, reactant mixture, and molecules travel through this reactor and then composition is measured by mass spectrometry. So this construction methodologically is simple, technically is very complicated, invented 15 years ago, and in different modification you can find this construction in about more than 15 labs of the world. Germany, Belgium, England, France, Switzerland, China, Japan. Okay, now I just show you how it works. So this key characteristic, pulse intensity. Pulse is quite tiny, 10 13 molecules per pulse. 10 minus 8, it's outlet pressure, but pressure inside is 10 minus 3, 10 minus 4 torr. So we have inert, reactant, and product. This is exit flow versus time. Exit flow, it's number of molecules at the exit of reactor. Okay, so this is ordinate, it's number of molecules, time. Okay. Sorry for noise. Some people like it, some no. Okay. So we have the many people in this audience know the idea of tap machine. Is it clear? Because did you understand this idea? Idea is very simple. We have some catalyst bed, and at exit we producing, at the inlet we producing pulse, and molecules just travel through the catalyst. That's it. Okay? But in this case, in difference from traditional device, CSTR, we don't have convection. We have only diffusion. Okay? In diffusion, in this case, typically, nuts in diffusion. Do you know what this means, nuts in diffusion? It's diffusion which is governed only collision, like it's drunk-word behavior. The interaction of drunk word with wall of channel. No collision. It's assumption drunk people don't collide. Crazy assumption. Okay, so, and then idea, but what is important in Knudsen diffusion is well defined. Diffusion under, under molecular diffusion, under normal condition, have complicated dependence on composition, temperature. Knudsen diffusion, well defined. This diffusion doesn't depend on composition, depends only on size of this channel. So, and then John Gleaves and me invented this proposed the idea of interrogative kinetic approach. What does it mean? The main idea is combine two types of experiment. One is state-defining experiment, in which catalyst composition change insignificantly during the test. Another state-altering experiment in which catalyst composition is changed in control moment. What does it mean? If you're doing one pulse experiment or small train of pulse experiment, your catalyst composition doesn't change. It's like one hair polish. Okay? So your perturbation is so insignificant, catalyst doesn't change, you characterize state. But if you're doing multi-pulse experiment, catalyst does change. Okay? And you know how it's changed because you know total amount. You know amount per pulse and you know amount of multi-pulse. Okay. So let's go to the data. This is data furan oxidation, and it's furan conversion. Furan goes to maleic, acrolein, CO2, and CO. So we have furan conversion. You have, CO2 yield. Okay. You have acrolein yield. Okay. And you have what else? You have maleic. This is maleic. Okay. So it's typical. It's furan conversion or product yield versus pulse number. But we can find the total amount of transformed furan. We know it because we know multi-pulse, and then we are able to transform this we are able to transform this axis to axis catalyst alteration degree. For example, we have scale, total amount of transformed furan or consumed oxygen can be considered as a scale. And then we can consider here, it's like, we can say it's unity, because at this point all the catalyst is oxidized. We can say zero of catalyst alteration, and then here it's like 1, because we consider is like catalyst completely reduced. Okay, so if you use scale catalyst alteration degree, it's good scale, it dimensionless. So to characterize something, some simple lesson. To characterize something, you need to have scale. In this scale, total amount of consumed, for example, furan, which you need to reduce surface. So you need to have scale. Okay, and then you have scale, you can plot the same furan conversion, product yield, and maleic, and CO2, maleic, and you have Crowley's yield. Okay, so these characteristics don't depend on mechanism. This characteristic we call model free. Okay, next step, we can plot portion of furan molecule converted into particular product versus this catalyst alteration degree. So this is 0. Catalyst is the same. It's not changed. Here, catalyst completely changed. It is reduced. And then this is like we have this probably CO2. This is it's not because it's like blue. This is maleic. This is acrolein. This is some maleic and acrolein. And it's interesting. CO2 it's approximately equal to maleic and acroleic. It's like in many cases it's like this. So we know portion of maleic converted into particular profile. It's very important to use generally reaction multi-road, but I like to use such overall equation. I have a good relationship with Professor Tionkin, and he was advertising this type of equation in which you have not multi-road reaction, but only one reaction. This stoichiometric equation function on selectivities. It's very interesting. It's very useful type of reaction, type of presentation. Then you have amount of oxygen removed per furan molecule versus catalyst alteration degree. So why we take it? We can find because we have selectivity and we easy transforming this data into this data. So this is like we can call this presentation like passport of the catalyst. It's like catalyst dependencies versus alteration degree. Okay. And then we can find total amount of oxygen consumed in the reaction was approximately the same for all 4 reactant molecules. It's very important because in this case we are understanding we have consistent data. If we're using any reactant calculation, we have approximately the same amount of consumed oxygen. Okay. So, is this piece understandable?
I'm sorry, I have a question.
Okay.
What means total amount of active oxygen consumed in the reaction was approximately the same? It means that CO2 consumed the same amount of oxygen?
No. I just, I can use different kind of molecules, reactant. Not only sorry for this misunderstanding, because I, cut one slide. We are used not only for N, we use butane, propene, different,
okay.
And then when we use, I just cut one slide. And when we're using different molecules, we are understanding amount of taken oxygen is the same. So, now, 3 requirements. You remember I talked about some requirements for preparation. In fact, these requirements have kinetic character. And then 3 requirements. First, we need to have uniform chemical composition within catalyst zone. Then insignificant catalyst change during the non-steady state. Then control of reactant amount stored released by catalyst in non-steady state. So we need to have, remind you, uniform active zone, insignificant change during one experiment, and then control amounts of stored, released product during the multi-pulse experiment. Now let's little bit, because I have this detail table partially in my paper in review in Journal of Catalysis. By the way, I recommend you to read this review because it's not my review, but all the issue, it's like encyclopedia of contemporary catalysis. Let's compare different strategy of kinetic characterization. I remind you, CSTR, continuous state tank reactor, plug flow reactor, surface science, and TAP. Domain working conditions, normal condition, high and ultra vacuum, TAP, 10-3, 10-4 torr. Applied kinetics, CSTR gives information about industrial catalysts, PFR gives, surface science doesn't provide, ICA provides, we can say carefully, some. Observation regime, steady state, PFR, steady state, non-steady state, surface science, blah, 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 TAP, unsteady state. We can use steady state measurements in TAP, but advantage of TAP, of course, it's unsteady state. Then what we can compare applied kinetic separation of chemical reaction and transport. You can say in CSTI it's well-defined convection, perfect mixing, but it's assumed, and in literature always discuss validity of domains because we have turbulence, and turbulence is not easy to define precisely. In PFR, I consider it's good, well-defined convection. In surface science, no convective transport. In TAP, we have well-defined diffusion. Now, CSTR, catalyst composition in PFR. Catalyst composition does change, of course. Surface science, we can observe change. TAP, as I told, insignificant change. Okay? Uniformity. Uniformity is assumed, but it's difficult proven for CSTR. For PFR, there is no uniformity. For surface science, we can characterize. Sometimes it's not uniform. For TAP, 3-zone, which I demonstrated you, catalyst composition is non-uniform as well. And finally, amount of gas reactants. For CSTI and PFR, without details, it's difficult to measure. For surface science, of course, it's possible. For TAP, it's possible. Okay? Model 3, we can talk about this later. So, if you have how to extract rate, if you have batch reactor, rate is identified with derivative. If you have CSTR, rate is identified with difference inlet and outlet. And for steady state, and we can extract derivative. For PFR, we can extract some, but it's not easy. We should assume rate. And finally, for diffusion, for TAP, we can extract rate because diffusivity is well defined. Okay, so it's not so difficult to extract this rate. So, as a result of this careful, maybe too careful comparison between different kinetic devices, what is the result? There is no ideal device. No. Even TAP is non-uniform. Okay, what to do? I remind you 3 requirements. ideal uniform zone, no disturbance in single experiment, and control of measurement or uptake or release in multiplex experiment. And then no ideal device. What to do? We need to invent ideal device. Let me present you ideal device. Ideal device is thin zone tap reactor. What does it mean? We are making our zone so thin. I tell you in advance what does it mean thin. It's about 1/10 of length. If you have this 3 inches, you should have 0.3 inches like here, and also diameter is like 1/4 inch, sometimes. Okay, and if our analysis in theory, it demonstrates if you have if you have such thin narrow zone, this zone provides good mixing within this zone. And you have the same, you can say CSTR, but in difference from CSTR, you have the reason of this CSTR. It's not convection, it's just diffusion. And we have, inlet flow, outlet flow, and difference between inlet flow and outlet flow, it's, you can say, rate. Like in CSTR, you have inlet convection, outlet convection. In this case, you have inlet diffusional flow, outlet diffusional flow. But conversion can be, can be estimated very typical. If you remember something from chemical engineering, conversion equal K time divided by unity plus K time. Okay, this is conversion. But time in this case, it's diffusional time, not convectional time. Convectional time, as you remember, length divided by velocity. In this case, it's like length squared divided by diffusivity. Okay, so, and when we characterizing our measurements, we have so-called moments. I just go to, this is typically, we have information, primary information, it's exit flow versus time. Exit flow versus time. Area, this area is like, zero moment. Okay, this is like integral, you have 0 moment. And then first moment, it's time multiplied by exit flow integral. And second moment, it's time squared. And what the physical meaning of this? Unity minus 0 moment is just conversion. First moment divided by 0 moment, it's residence times. Second moment divided by first moment, it's characteristic of time delay. Very important characteristic. Okay. So, we have, it's again, so from 0, first and second moments, we are easily calculate conversion, selectivity, product yield, and residence time, and then using theory, I just make hint of this theory, but I'm not going to explain detail. We are extracting apparent rate constant, apparent time delay. It's very important because time delay is characteristic of intermediate, something going on the surface. Because of that, we have delay. And then apparent intermediate gas constant, physical meaning is some interplay between gas and surface intermediate. For example, if reaction is irreversible adsorption, this apparent intermediate constant equals 0. If you have only one reversible reaction, it's constant equilibrium. But if you have sequence of steps and some of them reversible, you have some function of constant. Okay. Now, I just show you state defining regime and state altering. State defining regime, it means practically no change between these pulses. No. And then you can say observed responses are essentially the same. Okay. So it's state-defining regime. Its state-defining regime can be, we can say, insignificant change in the pulse responses within train of pulses, or you can say it's not, maybe not good picture, but we can say you change pulse intensity, but exit flow is the same. In this case, you can say no change, state-defining regime. But typically, state-defining regime, it means you have no change in exit flow. It means state is the same. Okay. But this state altering experiment, you have change of state. So you have gradual change of your exit flow. It's like this, maybe it's like this. Reactant is decreasing. Product also decreasing, for example. You have some change. Okay. Then to develop theory, we need to distinguish catalyst state substances don't change significantly during experiment and determine the catalyst state. And then catalyst dynamic substances, which typically considered as intermediate. Catalyst dynamic substances arise in the course of non-steady state defining experiment, and typically intermediate concentration much smaller than substances of the catalyst state substances. Okay. Also, theory assumption, rates of elementary reactions don't change as function of concentration of catalyst state substances, because we consider during one pulse catalyst doesn't change. But it also rates are linear with respect to small concentration of dynamic substance. This assumption is not general, but it's very often, accordingly, analysis of literature and my experience, linear mechanism, linear rates are often. And then we have equations. Equation rate consists of two terms. This this term relates to first idea, rates don't change, we have only gas concentration. And second, we have reaction with intermediates, which are also linear. After that, I show you how it's going in theory. In theory, we have idea state of catalyst. It means it doesn't change during one experiment. We have gas concentration, surface intermediate. Then we develop idea of state-defining experiment in significant perturbation. Then we're using linearity dogma. It means linearity with respect to gas concentration. Then we have general model kinetic expression, and theoretically we have so-called basic kinetic coefficients. And as I told you, apparent kinetic constant, time delays, can be considered as basic kinetic coefficients. Now, what is from experiment we have? From experiment we have for special reactor configuration, for example, thin zone, we are observing moments, and then from these moments we have the same basic kinetic coefficients. And then, if you need, we can take detailed mechanism of complex reaction. Okay. Now, let's little bit exemplify. We have the same furan oxidation over oxygen-treated VPO. We have portion of furan molecules converted into a particular product versus catalyst alteration degree. So we have CO2, maleic, acrolein. Okay. I'm just repeating the previous slide. Okay. What else? And theory gives us very simple characteristic: apparent kinetic constant versus catalyst oxidation degree. It's important characteristic. It's easy to find because I remind you, observed value is exit flow. Integral exit flow is moment. Okay, unity minus moment conversion. Using conversion, it's easy to find apparent kinetic constant. And this apparent kinetic constant different for different reactants, for furan, for maleic, for CO2, for acrolein. And we can say simple thing. Apparent kinetic constants very different for these three products. I can consider I have at least 3 rows. Apparent kinetic constants. Okay. Then I have, I know total amount of my taken oxygen. I can consider this total amount as a number of active sites, and then I can find characteristics which never been found in literature. You know turnover number? What does it mean, turnover number? Turnover number, it means in catalysis steady state rate divided by number of active sites. In this case, we can find non-steady state turnover number. We dividing this apparent kinetic constant, we can divide by total amount of uptaken oxygen, okay? And then we can find non-steady state turnover number. But then we can find apparent gas constant. It's for different substances, for furan, this is furan, this is maleic, this is CO2, and this is acrylic. Okay, but what is most important, we can find apparent time delay versus catalyst oxidation degree. We can find this characteristic at any state of catalyst, and what does mean time delay? I just remind you, it means something going on the surface. What's something going? Intermediate work. And then we have different time delay for different molecule. It means we have at least 4 intermediates. And what is interesting, at least 4 intermediates can be involved. What is interesting, this time practically doesn't depend on catalyst oxidation degree. Okay? Because of that, I can say, you remember I told you, because of distinguishing 3 apparent rows, I have 3 independent rows, at least 4 specific intermediate. Independence for CO2 time delay, and using this qualitative consideration, I can say I have 3 rows, maleic, acrylic, CO2. I have at least 4 intermediates, ZO, X, Y, U, and for CO2 I have independent way, additional center. CO2 is adsorbed on the another center. So, and we are using this mechanism, and then we are going to feed this mechanism. So, as a result, we have such analysis, such kinetic characterization. We have thin zone, and then we have state-defining experiment, 1 pulse experiment, in state-altering experiment, which changing state. For any state, we are going to have moment-based analysis, and for any moment-based analysis, we have integral state characteristic, its number of consumed gas, and kinetic state characteristic. It means I mentioned you apparent constant, intermediate constant, and time delay. And then we are identifying number of consumed released gas substances as a catalyst state. And then we are making assumption about mechanism. Then we distinguishing mechanism. We find dependence on the coefficient of catalyst state dependence. Then we are go to like the main mystery of catalysis, the structure-activity relationship. After our previous steps, we found some constants, and then we can go to physical characterization and relate this constant to activity. In my opinion, not early. Now, how many time I have? Back to catalyst preparation. Now, I think I promised you ideal kinetic characterization. Okay. But we need this catalytic. What for we need this characterization? For catalyst preparation. Okay. And 6 months ago, Dr. Gleaves, John Gleaves, who was inventor of first step modification, he, you know, completed, and he realized his dream to use pulse regime for catalyst preparation, not only for characterization, but for catalyst preparation. What does it mean? Typically, how to change oxidation state? You can change oxidation state using pretreatment, steady state flow of oxygen, or pulse addition of oxygen, or multi-pulse reduction of oxygen state. And for example, we can use chemical vapor deposition. It's typical, you know, interference with deposition kinetic. But what is, it's very useful, very, you know, practical method, but one disadvantage, it's difficult to control and repeat. You know, I reminded many times, catalyst is surface phenomena, but we should somehow monitor what is surface composition. In this case, we are not able to do that. It's impossible to control. In some cases, it's unique cases. It's possible, but generally not. Okay. Second, typical, you know, wet impregnation. Wet impregnation, it's also a method for altering metal atom surface composition. But in this case, it's also difficult to control and repeat. And what is tap method? Maybe another. We, of course, have methods for altering metal atom surface composition using atomic beam deposition, surface science method. In this case, certainly it's possible to somehow determine surface composition. But generally, this method has not been applied to technical materials. It's applied to model crystals, model plane, you know, 001. In few cases for you know, crystal of oxides, but it's not for industrial cases. Okay. This is John Glyph's idea, creating nanoscale concentration gradient of transition metal species on bulk metal oxide catalyst. So what is main principle of experiment? You have laser beam. In our case, it's excimer UV. You have transition metal source, target, it's about 3-inch diameter. And then we have atomic beam, typically, for example, it's niobium, vanadium, tellurium, okay? And then, as a result, normalizing this beam, we know exactly amount of these particles, of these atoms. Okay. These particles are, you know, these particles are going to vibrate back, and at vacuum. And it provides guarantee for uniformity of deposition, and we know exactly the total amount of these molecules. Okay? So, as a result, we have a new TAP2 multiple reactor system, atomic deposition system, which works already about 6 months. Okay? So we have 2 chambers. This is chamber, deposition chamber, and reactor chamber. Reactor chamber is traditional tap reactor for kinetic characterization. And this is like, you know, you have, this is target, this is holder, you know. So we have 2 functions, preparation and characterization. So this is real stuff. Okay, we have deposition chamber, it's like this. And tap reactor chamber, diffusion pump, mass spectrometer. Okay, so laser spot, you can see sample folder, copper. Okay, and then we have some results. For example, we have butane reaction over VPO catalyst. It's like we have butane conversion, pulse number, and time. 3D. And if you have copper deposition total coverage less than 0.05 milliliter, it's changed. It's 3D plot, it's not so good, I show you just a little bit. So the same change. So it's just to understand you have change. Butene conversion, butene over VPO, and the same butene conversion, VPO modified by tellurium. Okay. As a result, you have, for example, furan yield versus pulse number. Okay. So this is yield, this is pulse number. We can plot using catalyst alteration degree, but it's like rough data, and it's clear at some alteration degree, at some pulse number, modified catalyst has yield higher than non-modified catalyst. You have tellurium, you have copper. In this case, okay, so it's just typical curve, okay, and we have for these 6 months we have. I'm not going to exaggerate, but we have experience working with company modifying catalyst, and we have, some clear maximum of yield and selectivity versus percentage of modified. So, and we consider it's our strategy. It's strategy to use two functions of pulse organized preparation, and then pulse, organized characterization, and then go back and forth, like evolutionary approach, to find really optimal concentration of modifier. In fact, it's done for selective oxidation catalyst, but I could not find reason to apply this method for any heterogeneous catalytic problem. In our case, we are using non-porous catalyst, selective oxidation catalyst, but we have experienced analysis of diffusional process in zeolites, distinguishing interparticle diffusion and interparticle diffusion. Then, because of, it's another problem, I talked to you only about TAP method, but in fact, because we have collaboration with companies, we are always go back and forth from TAP to plug flow reactor, and in plug flow reactor we are doing both steady state experiment and step response experiment. It's very interesting to combine and to correlate step response data with pulse response step data, but it's another bridge. Okay, in fact I finished. I spent 45 minutes, but I'm ready to answer some questions if you have. Okay.
Yeah. Do you have any limitation on like temperature or something?
Yes, we have energy of activation. We are changing temperature. We are repeating all this experiment under different temperatures.
But do you have any limitation how high you can get your tap?
For example, I show you example. We have we analyzed methane oxidation. It's 800, 900 Celsius. I don't consider we are able to do 1500, but I don't know. But up to 1000, it's okay.
On the catalyst preparation side, using the laser and the metal, are you limited with the type of metals that you can use, or can you use anything?
In fact, it's not my part. My part is I'm just in this moment it's inventory, John Griff's inventory. I'm just advertising. But in this moment, we have target for transition elements. It's what we have experienced. I just mentioned it. It's vanadium, it's tellurium, it's copper, niobium, maybe something. It depends, it takes time. Maybe we need to change laser characteristic.
Have you looked at the properties of your modified VPO?
005 copper, 005 on the layer of copper atoms. In fact, I don't remember what I know exactly what is. I just asked. Particle size for this case was about 150 to 100 micron particle size.
And you just calculated this many layers?
Yes.
Just calculated
Yes.
based on surface area and amount of
Yes.
copper.
Yes, we just calculate it because we know total amount and we estimate it. In fact, I'm not going to explain. If you ask me, I explain more about theory. If you don't ask, I'm not going to explain because I have macro version with some theoretical stuff. Okay.
What is the requirement to ensure that you have Knudsen diffusion in your tap?
It can be proven, in fact. First of all, you prove with no reaction, okay? You prove no reaction, you pulse something, and you change pulse intensity. If pulse intensity doesn't influence your exit flow, you're in Knudsen diffusion. That's it. Okay. So influence, pulse intensity, composition influence. You can change. Inner gases. For example, instead of argon, use krypton. No influence. You're in Knudsen diffusion. It's quite simple.
So when you reach Knudsen diffusion, the approach you use is low pressure and
not completely low. It's not 10
Yeah.
minus 8.
Yes,
It's 10 minus 3.
not very low, but a
Yeah,
little
it's
bit
10
lower.
minus 3. It's okay. But yeah, it's true. We are
What else to
More?
achieve?
more.
Yeah.
I remind you, we are always comparing this approach with normal conditions. We are always doing plug flow, okay, and plug flow step response. For example, we like combine pulse response step and step response, step response for plug flow. In many cases, we have good agreement. For example, for oxidation, I can even generalize. If you have irreversible reaction, so-called, pressure gap. Pressure gap, it means surface science data cannot be transferred into normal conditions. This is it. But if you have irreversible reaction, you can in many cases transfer irreversible. But if you have reversible reaction, it is difficult, and you should somehow find this constant and irreversible condition and then go back and forth. So, in fact, we have three handles: tap, plug flow, and steady state. But advantage tap, you understanding something about dependence on catalyst, in simple case, reduction oxidation. If you don't have, tap data, you could not. It's very difficult to say. You can find some ideal dependencies using dependence, kinetic characteristic versus oxidation reduction rate. Then you can go normal conditions, and then you can test this characteristic, and combine this characteristic, compare. But first of all, such.
What is the best time resolution can you accomplish in this message?
It's 200 microsecond pulse response. 200 microsecond, pulse. It's quite, 10 minus 4 seconds.
Is the same order of magnitude of the half time of intermediates?
It seems yes, because typical intermediates, I think, not 10 minus 6. It's 10 minus 3, 10 minus 4.
Did you try to compare conventional method of preparation of catalyst and the method which you try to use in this?
You know, what is the situation? We have about 6 months of this, you know, but first comparison, it's very clear, because I did it, this comparison. You know, if you use, for example, if you use wet impregnation, if you use chemical vapor deposition, you could not control surface concentration. You just could not control. You know, advantage of this method is you can relate kinetic characteristic to some surface concentration of you modify. In chemical preparation, in chemical deposition method or in vent impregnation method, you could not relate. You don't know. This is just new possibility. What about surface science? We can relate, but surface science, it's about, you know, 001 plane, it's about model crystals, it's about industrial catalysts. The most interesting feature which proposed by John Greaves was we take industrial catalyst, okay, and this industrial catalyst can be, you know, deposited by, you know, some transition metals, and we know exactly how many we have, you know, surface concentration. And then we can go to kinetic characteristic. We just, we maybe don't need 10 in this case. We can even simplify problem. We just can use steady state, which favor it for people, and use this, you know, like the position chamber, you know. What I just like, my you know, answer is a little bit detailed, but yeah. And in addition, as you know, there is so-called combinatorial catalysis. I don't like this word because it's better to use high throughput catalysis, because even in combinatorial catalysis you don't have all the combinations. Okay, but combinatorial catalysis, people doing steady state, but people don't extract information about non-steady state. But non-steady state is important information because, look, for example, typical reaction, catalytic reaction, which I know, typically low energy of activation for adsorption and high, but not too high, energy of activation for reaction. So, in this case, you know, typical favorite strategy is like two-stage reactor, cold adsorption, but hot, but not too hot reaction. Okay. So, but to do that, we need to know characteristic of steps. We need to analyze. We don't need to have detailed mechanism. We need to find some simple non-steady state knowledge. And it's impossible to extract this knowledge using steady state data.
I agree with them when you look at the combinatorial catalysis. Excuse me for that word, you don't like it. It's a quite, let me say, it's not a very intelligent method. You don't understand a lot about what happens on the catalyst, and you don't know exactly why the catalyst is working these conditions a certain way. But at least you get huge amount of information when you're going to develop or optimize catalyst. How you would describe your method, the combined method here? Yeah, the combinatorial.
You know,
How much time or how much experiments you would need to at least optimize?
You know, it depends on how. You know, I tell you a story. In catalysis, we don't have theory. In fact, this is true. We don't have theory. And when I can say, my advisor, academician Boreska, he asked people who prepared catalyst, did you try yttrium? And they say, we tried. Did you try neodymium? We tried. Did you try praseodymium? No, we didn't try. Try praseodymium. You know? So, generally, this story about catalysis is still true. You know, we are still in the situation we don't have general theory. What we have, okay? First of all, we are able to improve methodological level of measurement. You know? And what is here, it's in our approach, we are going to create more systematical way for catalyst characterization. For example, I was very surprised previously. I did not find precise measurement activity versus reduction oxidation degree in many catalytic systems which we are doing. So, first our result is we are able to characterize catalyst versus alteration degree. For example, for catalyst we have two characteristics: reduction oxidation and acid basic properties. Sometimes they interwoven. Let's characterize, just characterize, and we will understand many things when we characterize in simple way. Such characterization, it's not time consuming. For example, I can say,